Sewage-fed fisheries and its importance. Pollution affecting fishery water with special reference to oil spills, domestic pollution, industrial water pollution, radioactive waste, bioaccumulation, and biomagnifications. Sewage-fed fisheries and its importance. Sewage-fed fisheries represent a cost-effective and sustainable model of aquaculture that utilizes treated or semi-treated domestic sewage for fish culture. This method not only offers an economical means of fish production, but also contributes to the secondary treatment of sewage through the bioremediation potential of aquatic organisms. These systems are highly nutrient-rich due to the organic load in sewage, which promotes plankton growth, the primary natural food source for many fish species. This leads to enhanced fish productivity, often without the need for artificial feed inputs. A classic example of successful sewage-fed fisheries is the East Kolkata wetlands, where Indian major carps, catla, rohumrigal, tilapia, and common carp are cultivated. However, effective management is essential to ensure the safety and sustainability of such systems. Sewage must be appropriately diluted with fresh water to maintain desirable levels of dissolved oxygen, ideally greater than 5 milligrams per liter. Liming is regularly done to control pH and pathogenic microbial populations. Periodic monitoring of biochemical oxygen demand (BOD), chemical oxygen demand (COD), coliform count, and heavy metal content is essential. Care must also be taken to ensure that fish harvested from such systems are subjected to purification periods before marketing to reduce microbial and chemical contamination, thus ensuring public health safety. Pollution affecting fishery waters. Fisheries in India and globally are significantly impacted by different types of aquatic pollution. Understanding these pollutants is crucial for fisheries professionals and environmental managers. 1. Oil spills. Marine and coastal fisheries are especially vulnerable to oil pollution caused by tanker leaks, drilling operations, or shipping accidents. Oil forms a layer on water surfaces, blocking light and oxygen exchange. It coats the gill surfaces of fish, impairing respiration. Polycyclic aromatic hydrocarbons, PAHs, from oil can enter fish tissues, leading to chronic toxicity, reproductive failure, and carcinogenesis. 2. Domestic pollution. Untreated or partially treated sewage introduces organic matter, nutrients, mainly nitrogen and phosphorus, and pathogenic microorganisms into water bodies. This results in eutrophication, which causes algal blooms, and severe oxygen depletion, hypoxia, ultimately leading to fish mortality. Excess ammonia and nitrate concentrations also have a direct toxic effect on fish. 3. Industrial pollution. Industries discharge harmful chemicals like pesticides, heavy metals, Hg, Cd, Pb, dyes, and acids into water bodies. These pollutants interfere with the osmoregulatory functions of fish, damage gill and liver tissues, and often result in bioaccumulation. Thermal pollution from power plants also affects fish by altering enzyme activity, metabolic rate, and breeding cycles. 4. Radioactive waste. Although less common, radioactive isotopes from nuclear power plants or hospitals, like iodine-131 cesium-137, pose serious ecological risks when discharged into aquatic systems. These elements accumulate in fish tissues, leading to DNA damage, mutations, and long-term population decline. To mitigate such pollution, it is imperative to enforce environmental protection laws, establish effluent treatment plants, and promote awareness among industries and local communities. The role of pollution control boards and regular biomonitoring is central to maintaining water quality. Bioaccumulation and biomagnification. Bioaccumulation and biomagnification are processes that result in the concentration of toxic substances within aquatic organisms, including fishes, over time or along trophic levels. Bioaccumulation refers to the gradual buildup of toxins like mercury, lead, or organochlorine pesticides, e.g. DDT, in an organism through ingestion or absorption from water. These compounds are lipophilic and are stored in fatty tissues because they are not easily excreted or metabolized. For example, mercury bioaccumulates in predatory fish like snakehead and catfish, reaching concentrations that may be harmful to human consumers. Biomagnification occurs when these accumulated toxins increase in concentration as they move up the food chain. Small aquatic organisms, like plankton, ingest micro-level toxins, which are then consumed by small fishes, which are further eaten by larger carnivorous species. For example, a pesticide concentration of 0.0001 ppm in water may become 0.01 ppm in zooplankton, 0.1 ppm in small fish, and 1.0 ppm in larger fish like carnivorous carps or catfish. Both processes pose significant health threats to humans and wildlife. Regulatory measures include the limitation of pesticide and heavy metal usage, better waste disposal practices, and the implementation of water quality standards as prescribed by agencies like the Central Pollution Control Board, CPCB, and Bureau of Indian Standards, BS. Conclusion. The environmental health of aquatic ecosystems is closely linked with fish production and public health. Sewage-fed fisheries showcase a model of resource recovery and ecological aquaculture when managed properly. However, the rise of different forms of pollution, domestic, industrial, oil-based, and radioactive, highlights the need for integrated water resource management. Processes like bioaccumulation and biomagnification emphasize the risks of toxin entry into the food chain, necessitating scientific monitoring, environmental legislation, and sustainable aquaculture practices.